Thermal dissociation of an atom. An ideal gas of atoms is confined within a box with edge lengths L sub x, L sub y, and L sub z. The whole system is in equilibrium at absolute temperature T. The mass of an atom is capital M. An atom can dissociate into a positive ion A plus and an electron E minus according to the scheme A plus plus A minus. An ionization energy U is required to overcome the electron binding and achieve ionization. Focusing attention on an individual atom, it can thus be in two possible configurations. Call them U undissociated, D dissociated. Its energy is epsilon, where epsilon is the kinetic energy of its center of mass. The translational state of the motion of the atom can, as usual, be specified by a set of quantum numbers n sub x, n sub y, and sub z. When the atom is dissociated, it's dissociated into an electron of mass m and a positive ion of mass nearly equal to the mass of the atom, capital M. The interaction between the ion and the electron after dissociation can be assumed negligible. The total energy of the dissociated system consisting of two separate particles is then equal to the sum of the kinetic energy of the ion, kinetic energy of the electron, and ionization energy. The translational state of this dissociated system can thus be specified by six quantum numbers, nx, ny, nz pluses and minuses, ion and electron. Using the canonical distribution, find to within a constant of proportionality the probability that the atom is found among those of its states where it is in the undissociated configuration. So a few things to note here. We're talking about a free ideal gas. So these atoms are free even after they are dissociated. We are neglecting the interaction between the atoms. It is a free gas in a three-dimensional box, in a 3D box, with edge lengths Lx, Ly, Lc. Temperature is T. The mass of an atom is capital M. Now, when we have this ionization process, A plus plus E minus, so what changes here? Well, first we had the mass M, capital M. Now we have capital M and lowercase m, so that's the mass of the electron. So M is much less than capital M. Second, we have a change in the energy of the system. The energy was the epsilon kinetic energy of the undissociated atoms, and here we have the kinetic energy of the ions, kinetic energy of the electrons, and the ionization energy U. So the energy of the system changes when it is dissociated. And the number of degrees of freedom changes. I need three quantum numbers, n sub x, n sub y, n sub z, in order to describe the undissociated atoms. But here I have nx plus, ny plus, nz plus, nx minus, ny minus, and nz minus, because I have to describe the kinetic energy of the center of mass of both electrons and the ions. So that pretty much summarizes everything. So one thing I'd like to stress here is free atom, ion, electron. So we always have free. There is no interaction energy between the ions and the electrons even after dissociation. Okay, so the first question was to find the probability of having it in the undissociated state. So for the undissociated state, if you write the energy levels for each quantum state, I have the energy pi square h bar square divided by 2. Mass of the atom is capital M, n sub x square plus over L sub x square plus n sub y square over L sub y square plus n sub z square over L sub z square. Now, the probability of being in quantum state R, according to the canonical distribution, is some constant c times exponential minus beta epsilon r, where beta is 1 over Boltzmann constant times the absolute temperature T of the system, and the system was in equilibrium. Now, how do I find the probability of having it in the undissociated state? So in the U state, all quantum states with energy epsilon r are possible. So I need to look at the probability of being in quantum state R, at quantum state R plus 1, at quantum state R minus 1, etc. So all of them. So the probability of being in the undissociated configuration is sum over all quantum states, the proportionality constant C exponential minus beta epsilon r. So if we rewrite this, the proportionality constant does not belong to the addition. The summation is over the three quantum numbers nx, ny, and z, starting from 1 going to infinity, exponential minus beta pi square h bar square divided by 2m, and then I will have nx square over lx square, ny square over ly square, and z square over lz square. Now you can see that I have three terms being added in the exponential, which allows me to write the probability of being in the undissociated state is a constant c times three partition functions zx, zy, and zz, where the ith partition function is given by a summation over the ni quantum number from 1 to infinity, exponential minus beta pi square h bar square divided by 2m ni square over li square, and I can be x or y or z. Now I'm going to approximate this partition function using an integral. So this partition function can be approximated as an integral from 0 to infinity for many quantum numbers starting from 1 or 0, doesn't matter, in the integral, exponential minus beta pi square h bar square divided by 2 capital M ni square over li square dni. So in order to perform this integral, I'm going to define let u square be equal to beta pi square h bar square ni square divided by 2 capital M li squared. So you can see that with this I will have 2u du will be equal to 2 ni dni multiplied with beta pi square h bar square divided by 2m li squared. The 2's will cancel. So I can see that with this I will have to substitute for Ni here. So what is Ni in terms of U? And here I can see that Ni is equal to 2m Li squared divided by beta pi squared h bar squared to the power 1/2 U. So I will have to substitute that in U du. So I see U du is equal to Ni dni. So for Ni I can substitute 2m Li squared divided by beta pi square h bar squared to the power 1/2 U. And then I have dni multiplied with beta pi squared h bar squared over 2m Li squared. So I can see then the u's will cancel here. I will be left with du. Du can be written as because I have the 2m Li squared to the 1/2 in the numerator and 2m Li squared in the denominator, I will get 2m Li squared to the 1/2 in the denominator. And the same is true for the other term. So I will have beta pi square h bar squared divided by 2m Li squared to the power 1/2 dni for du. Or I can write dni as 2m Li squared over beta pi squared h bar squared to the power 1/2 du. So I flipped the top and bottom because I've taken it to the other side to obtain dni. So now I'm ready to write the partition function zi in terms of u. Well, you can see that for dni I'm substituting 2m over beta to the power 1/2 Li square over pi square h bar square to the power 1/2 just gives me Li divided by pi h bar, and then integral if n goes from 0 to infinity, u also goes from 0 to infinity, right? U equals 0, n equals 0, u is infinite, but n is infinite. So I see this relationship. So this is exponential minus u square du. And this integral we have seen before. It's the integral of a Gaussian, and it is equal to square root pi over 2. Therefore, I see that my partition function zi becomes 2m divided by pi to the power 1/2 Li divided by pi h bar multiplied by square root pi over 2. So this can be written as, because I will be obtaining a square root pi in the denominator, and because I have a 2 in the denominator, so that's going to be coming into the square root as 2 square. So this can be written as capital M divided by 2 pi beta to the power 1/2 Li divided by h bar. Okay, so then I'm ready to calculate the probability of being in the undissociated state, it is C times Zx, Zy, Zz, which will be equal to C times capital M divided by 2 pi beta. Now this will be coming 3 times, so to the power 3 over 2. And for Li over h bar, I will have Lx over h bar multiplied with Ly over h bar multiplied with Lz over h bar. So there will be an h bar cube here. So Lx, Ly, Lz is the volume V. So I can see that probability of being in the undissociated state is C capital M divided by 2 pi beta to the power 3 over 2 volume divided by h bar cube. Now let's take a look at part B of the problem. Using the canonical distribution, find to within the same constant of proportionality C the probability that the atom is found among those of its states where it's in the dissociated configuration. So we're looking for another sum here, which will be for the dissociated configuration. Now similarly, we can do the dissociated configuration probability. That will be a summation over all quantum states where I have e to the minus beta epsilon r plus epsilon r minus, and the u was the ionization energy here. It's not the u I used in the previous part. So this will be equal to C times, now I can basically take the u out because it doesn't belong to this summation, e to the minus beta u sum over r. So this will be for the plus ones, r pluses, e to the minus beta epsilon plus for r pluses, and sum over r minus e to the minus beta epsilon r minuses for the electrons. So really I should be counting them separately, and because I have performed this already using the result in part A, I can write this probability as C e to the minus beta u. So that's precisely what I have performed in part A for this summation, and the answer was capital M divided by 2 pi beta to the power 3 over 2 v over h bar cube. And then I have performed it the same thing, but now I have to be careful. This is for the electron mass has changed, so it is lowercase m divided by 2 pi beta to the power 3 over 2 v over h bar cube. So this will be my answer for the probability. So I can rewrite this, if you wish, as C e to the minus beta ionization energy u. I have capital M, lowercase letter m, electron and ion, divided by 2 pi beta square, 4 pi square beta square to the power 3 over 2 multiplied by v square over h bar to the power 6 for the probability of having a dissociated configuration. Now let's move on to part C. Find the ratio. How does it depend on temperature and volume? So let's look at the ratio. Probability of the dissociated configuration to the probability of undissociated configuration. For the dissociated configuration, I have the constant c's will cancel, so it will be e to the minus beta u capital M over M divided by 4 pi square beta square to the power 3 halves v square over h bar 6, and then here I have capital M over 2 pi beta to 3 halves v over h bar cube. So this will give me first of all e to the minus, so let's also substitute for beta 1 over kt, u over kt, and then I will have for the capital M term will be cancelling completely. I will have the lowercase m term mkt over 2 pi over kt. So it's actually, I have operated the kt, so it is kt over 1, so that is 1 over beta mkt over 2 pi, and then I will have h bar remaining here, so h bar cube remaining here, so it's going to be h bar square to the power 3 over 2 multiplied by the volume V. So this will be the ratio. For beta, I have substituted 1 over kt. So in the ratio, I obtain m over 2 pi beta. For beta, I substitute 1 over kt. So it's mkt over 2 pi. And then I have an h bar cube remaining outside. So for h bar cube, I can write this as h bar squared to the power 3 over 2. So that goes inside, and then I have a volume remaining, so that therefore I have the temperature and volume dependence of this ratio explicitly written this way. Now let's move on to part D. Now consider the whole gas containing capital N atoms. So we have capital N atoms. Suppose that a mean number of these are dissociated, N bar dissociated. Then there exist in the box N bar ions, N bar electrons, while the remaining capital N minus N bar undissociated. A dissociated configuration of an atom can then be realized in N bar square possible ways and undissociated one in capital N minus N bar possible ways. By approximate reasoning similar to that of problem 4.24, one can then write the ratio of the probabilities PD over PU N bar square over N. Find an explicit expression for N bar over N in terms of the absolute temperature and density of the gas. Okay, so how does this actually work? So we have N bar ions. So we have an ion plus electron with a minus sign. So we have the first one, and the second ion and the second electron, etc. So if you remember, we can group the first ion with the first ion with the second electron, etc. So for each ion, we can have the corresponding electron out of N bar electrons, any one of them. So for the second one, any N bar of these electrons. So we have N bar square possible ways of obtaining N bar ion electron pairs. So also for capital N minus N atoms, so we have basically no matching with these ions and atoms. So we have capital N minus N bar on this dissociated atoms. Dissociated atoms. So we have capital N minus N bar ways of obtaining dissociated atoms. So we don't have matching of pairs like the one we had over here. So therefore the probability, according to the problem statement, of dissociated to undissociated probability ratio PD to PU is N bar squared divided by capital N minus N bar, and since capital N is much greater than N bar, this is approximately N bar squared over capital N. So what I would like to know is what exactly is this? So probability ratio I have calculated in part C. It was equal to mkt divided by 2 pi h bar squared to the power 3 halves volume e to the minus u over kt. Now with this I can calculate n bar. N bar will be equal to, now I take the root to 1/2, so another square root, mkt over 2 pi h bar squared to the power 3/4, and then I will have e to the minus u over 2 kt, and then I will have square root of capital N v. So what is the ratio n bar over n, capital N? That's what we were supposed to calculate in terms of absolute temperature and number density. So that will give me mkt over 2 pi h bar squared to the power 3/4 e to the minus u over 2 kt. Now I will have square root v over n here. So when I multiply it by square root, when I multiply the bottom by capital N, I get square root v over n instead of square root nv. So that's basically the dependence on the ratio v over n, or actually the problem is asking me explicitly the dependence on n over v. So this would be then mkt divided by 2 pi h bar squared to the power 3/4 e to the minus u over 2 kt n over v to the power minus 1/2. And let's look at part E. Part E, ordinarily Kt is much less than the ionization energy. Under these conditions, would you expect most atoms to be dissociated or not? Well, if you have a low energy in the system, when Kt is much less than U, we would expect most atoms to be undissociated in the lower energy state. So that would be because the ionization requires some energy, we would expect most atoms to be in the lower energies, lower energy levels, close to the ground state, i.e. undissociated, because it requires some energy to break the bonds and release the electron and the ion. Now let's move on to part F of the problem. Part F, suppose that Kt is much less than U, but that the volume of the box is made arbitrarily large while keeping the temperature constant. Would most atoms then be dissociated or not? Give a simple physical explanation. Now, as V increases, T constant, at constant temperature, if you look at the ratio in part C, the ratio of the probabilities of dissociation to undissociation is V. So we will have this ratio increasing. Probability of dissociation increases. So most of the atoms would now be dissociated. Okay, so by increasing the volume, the probability of the dissociation increases. So why is that so? Because we have a V square term in the probability of dissociation. We have both electrons and ions acting independently of each other. So so they see the full volume of the system. So it's because of that we have most atoms being dissociated. And now part G. Inner part of the sun consists of very hot dense gases, while its outer corona is cooler and less dense. Studies of spectral lines of light from the sun indicate that an atom may be ionized in the corona and yet be unionized in regions closer to the sun where the absolute temperature is much higher. How do you explain these observations? So even though the temperature is higher, it can be, we may see undissociated atoms inside. So inner part is dense. We have a V small, the volume is small. So an atom may be not ionized. Since we have a dependence on the ratio, probability of dissociation to unionized is proportional to V. So if you look at this probability ratio, it is proportional to kT to 3/2 e to the minus u over kT and V. So if V is very small, extremely small, then this probability is proportional to V, can be small, is small even though the temperature is higher. But in the corona, we have V is large, so even though the temperature is lower, we see that the probability of dissociation increases with V. Therefore, an atom can be ionized in the corona even though the absolute temperature is lower. So the question is, which one will dominate? So if you look at the ratio of the probabilities, how much lower is the temperature and how much higher is the volume? Since the volume is much greater, so the temperature, the change in the temperature, so basically this is telling us that the delta T from the inner parts to the corona, the change in the temperature is less significant compared to delta V. The change in the volume is much larger than the change in temperature, and therefore we see that it's more significant and it dominates the behavior, and the probability of dissociation may increase in the outer parts of the sun. Okay, so to sum up, we talked about thermal dissociation of an atom, where an atom has mass capital M. In the dissociated state, we have an ion which approximately the same mass, but electron mass lowercase m less than capital M. It takes some energy, the ionization energy, to cause the dissociation, and then in the undissociated state we only have the kinetic energy of the center of mass of undissociated atoms, which are shown by 3 quantum numbers. For the dissociated case, we have electrons and ions whose kinetic energies are shown by 6 quantum numbers, and we have plus the ionization energy required. Now we looked at the probability of having an undissociated atom. So you have to find the corresponding energy levels, and we have the particle in a 3-dimensional box states. The energies were calculated. The corresponding probability is canonical distribution, C times e to the minus beta ER. And to be undissociated, we need to take into account the possibility of being in all R. R goes from 1 to infinity, all possible states. So we need to look at the quantum numbers nx, ny, nz going from 1 to infinity, and calculate the corresponding canonical distribution Boltzmann factors, C times exponential minus beta epsilon r, summed over all possible states. And I have approximated these summations using an integration, because I'm going over all possible states. I can see that the probability of undissociated configuration is C times the product of 3 partition functions for x, y, and z, which I calculated to be capital M over 2 pi beta to the power 3 over 2 v over h bar cube. Then we have repeated the same thing for the dissociated state. This time we have the additional e to the minus beta u factor, and the same calculation is performed for electron and ion, giving us capital M times M. So that's the difference, because we have to replace the mass with that of the electron for the electron case, divided by 4 pi square beta squared to the power 3 over 2 v square over h bar 6. When we take the ratio, we see that we have an e to the minus u over kt factor, and temperature to the power 3 over 2 factor, and the volume factor coming into play. So and we have also when we have n bar electrons and ions, there is an n bar square possible way of matching these. So we have n bar square probability of having the ratio, the probability of having a dissociation would be proportional to n bar square, whereas we would have probability of unionized atoms would be capital N minus n bar, because we're not matching pairs like we did for interstitials and empty slots, for example, in problem 24. So this ratio gives us, for n bar over n, capital N, a temperature dependence T to the 3 over 4 e to the minus u over 2 kt, and volume to the power 1/2. And when kt is much less than u, if the temperature is very low, we would expect that the atoms would be in their lower possible energy states. That would mean undissociated. As the volume increases at constant temperature, this probability ratio increases, so most of the atoms would now be dissociated with volume. And if you look at the sun, we see a manifestation of this in the spectrum that is measured. We see that the inner part has a low volume. Even though the temperature is higher, the volume dominates, and we can see that most of the atoms will be dissociated, uh, will not be dissociated in the inner part, sorry, but in the outer part the volume is large, so most of the atoms would be dissociated. So even though the temperature is decreasing from the inner parts to the outer parts, because the change in volume is so big, we have the probability of dissociation increasing as we go to the outer parts of the sun.